So earlier we talked about what Milankovitch cycles are, and also why we're interested in them is kind of what I wanted to get to is to describe why we study these Milankovitch theories is because what we as scientists are looking for with as we study climate is what is actually considered normal. And so in order to understand what is normal, or if we are different than normal today, if our climate is changing truly because of human interaction, is we look at the past. And so Milankovitch cycles are one of those ways that we look at the past. This is geologic time, so these are really long, slow changes. But what you'll find is that we try to use these parameters to help us explain when did we have these ice ages and how did they happen. And so we have these three cycles that we already talked about. Eccentricity is, again, the elliptical variation that we may see. That happens about every 100,000 years that we have some variation within our orbital ellipse. We have the tilt, which occurs every 41,000 years. That's our obliquity. And our precession, which is kind of that wobbly top idea. And how precession affects us is about every 23,000 years. And so when we put this into the context of having climactic changes due to normal natural Earth cycles, we would be interested to see how and where we are among these types of cycles. Because this would definitely change our latitudinal seasonal distribution of our solar radiation, i.e. how much heat are we going to actually get from our sun in certain areas. So Milankovitch cycles, they occur less when we have less, or ice ages occur more often whenever we have less radiation. So when we look at these, you can see that there are, there's this top one, which is our eccentricity. Our obliquity is the second one. Precession is our third graph here. And then the one I want you to actually, and you can see that they have those variations. Eccentricity, remember, it has that every 100,000 years. Obliquity is a little bit more frequent, and then finally precession happens more frequently even than that. As we combined the overall impact of these waves, we see down here, this is our overall index, and you can see whenever we combine each of these cycles, when they overlap in their maximums and then their minimums, that we kind of get waves that are either amplified or are rarefied or canceled out. And so you can see that when we have had extreme temperature and extreme events where radiation was greater than or less than what we consider our baseline. So how does this compare to climate understanding? Well, it partially agrees with some of our observations, and we're going to talk about why it only partially agrees here shortly, but it doesn't answer everything for us, but it is one piece of this puzzle as far as rebuilding the climactic history of the Earth. So this brings us to some of these questions, and so what I'd like to do now is to take this Milankovitch information that you've been learning today and now put it into some geologic context, because again, we are comparing and using this really, really long-ranging cycles to be able to estimate or explain some of the known climatic differences in our geologic past. So when we think about long-term climatic change, we are thinking on terms of geologic change, and so we're looking at 250 million years ago. You guys probably have heard of Pangaea. It's the supercontinent when all of the continents were once together. We've actually had two Pangaeas in our geologic past, but most people know about the most recent Pangaea. And so I want you to kind of think about these Milankovitch cycles, how our Earth's tilt our eccentricity as well as our precession are all happening during these time periods, as well as the continents themselves are shifting around the entire surface of the Earth. And as today's continents drift apart, they move to different latitude bands. This is going to cause areas of our continents that we know of as being typically tropical per se. So like India here, where you can see India way up here. But in the past, it is very, very far toward the pole, the South Pole. This will change the way that we would look at the climate history of that particular piece of landmass. So not only does just the landmass's location within the latitude change, but also we have entirely new changes in wind and ocean currents. If you have a giant landmass, it definitely is going to cause these currents and these circular patterns with convection to completely change entirely. And so as we look at this, you can see that there's these circumpolar currents that have formed around Antarctica about 40 to 55 million years ago. That once Antarctica and that happened once Antarctica and Australia had separated. This prevented warm air to penetrate those latitudes towards Antarctica. So that absence of air, absence of warm air, probably accelerated the very first ice age that we know of, creating the Antarctic ice sheet. So definitely our climate history has a lot of factors involved with that. Not just our Milankovitch cycles, but also the geologic location of our continents were actually a really important piece of describing what our historical climate used to be. And so when we utilize this information, what I'd like to talk about next is how this actually relates to what we understand today's climate change is. Is this well outside of what should be expected? Because we've had some crazy stuff happen in our Earth's history based on Milankovitch cycles and based on our tectonic changes as well. These all make a complicated history or a complicated story to be able to tell that, hey, we have a normal climate change, or whether we have accelerated or unprecedented climate change that we see today. So, all right, we'll be continued for the next time.